Hello everyone. This lecture is exclusively recorded for second year BSc student of BK Birla College, Kalyan. This is mathematics class, calculus paper 1. In this lecture, we will state and prove the first fundamental theorem of integral calculus. So let me write down. This is SY BSc Maths 1. It's a calculus paper. So our objective of today's lecture is to state and prove first fundamental theorem of integral calculus. We will abbreviate it as first fundamental theorem of integral calculus. So let me write down the statement. If f is from closed interval a comma b to r be a real valued function and is Riemann integrable function, and continuous on closed interval a comma b, let g of x is defined as integral a to x f of t dt be an indefinite integral of f, then my function g, that indefinite integral g, is differentiable on open interval a comma b, and the derivative of g is basically, from this you can identify, or maybe one can guess, derivative and integrations are opposite in nature. So the derivative of g is basically f of x. So we are going to prove this theorem. So what is given? It is given that f is R integrable. It is also given that f is continuous and g is indefinite integral. So these three things are given. I need to prove that g is differentiable on open interval a comma b, and the derivative of g is f of x. So let's write down the proof. So let's write down what is given. So the very first fact is that f from closed interval a comma b to r is R integrable. Second is given that f is continuous on closed interval a comma b. In fact, a continuous function defined on closed and bounded interval is uniformly continuous. This is one of the rules. A function If it is continuous and if it is defined on closed and bounded interval, then it is uniformly continuous. So this would imply f is uniformly continuous on closed interval a comma b. So if it is uniformly continuous, then we can apply the definition. So what definition says? This says that for every epsilon greater than 0, there exists delta greater than 0. So we know what is the difference between uniform continuity and normal continuity. In uniform continuity, this delta depends only on epsilon, whereas in the normal continuity, the delta depends on epsilon as well as the point. So here depends only on epsilon, such that the modulus of x minus y less than delta would imply modulus of f of x minus f of y less than epsilon for all x comma y belongs to a comma b. So let me call this as some star. It is also given that the third given fact is g is an indefinite integer. So g of x is equal to integral a to x f of t dt for all x belongs to closed interval a comma b. What I need to prove is as follows. To prove that g is differentiable on open interval a comma b and g dash x is equal to f of x. So how we are going to prove? We will do one thing. We will take an arbitrary point from open interval a comma b and we will show that the function is differentiable on arbitrary point. If it is differentiable at arbitrary point, then we will say that the given function is differentiable on the entire open interval a comma b. So let p be any point from open interval a comma b. So we will prove that g is differentiable at p. That is to prove that limit as x approaches to p, g of x minus g of p upon x minus p, this limit exists and this limit should be equal to, we call it as g dash p, but here when I say g dash p, I wanted to show that g dash is same as f dash, so I should say this should equal to f at p. Okay, so let's to prove this we have to prove we have to prove this. So that is to prove that so as x approaches to p, then this entire as x approaches to p, in that case we have to show that g of x minus g of p upon x minus p approaches to f of p. So in terms of epsilon delta, how we prove this? So that is to prove that for every epsilon greater than 0, there exists delta greater than 0 such that if x minus p less than delta implies modulus of g of x minus g of p upon x minus p minus f at p, this entire difference is less than epsilon. This is what we have to prove, right? Okay, so now what we will do, whether this x approaches to p from left hand side and similarly x approaches to p from the right hand side, these two cases we will explore to prove this. So case 1, if x is less than equal to p, so this is my a, this is my b, so x is somewhere here, so x can be anywhere between a to p, so this is my p. So if x is less than equal to p, this would imply x minus p less than equal to 0. This would imply modulus of x minus p is basically minus x minus p. Okay, so now let me consider this difference, because I wanted to show that this difference is less than epsilon if x minus p is less than delta. So let me consider this difference straight away. So consider modulus of g of x minus g of p upon x minus p minus f of p, right? So which is same as, now what is g of x? So if we go to given fact number 2, it is given that g of x is equal to a2x f of t dt minus, what is g of p? We can even, again we can go to the second, here it is given g of x is given, so from this we can easily identify what is g of p. G of p is equal to a to p f of t dt, right? So instead of x we will have to write p, so integral a to p f of t dt upon x minus p minus f of p, right? So this x minus p can be taken outside, so x minus p modulus, then it will be integral a to x f of t dt minus a to p f of t dt minus x minus p f of p, bracket complete. This x minus p will be cross multiplication and then that will come outside the bracket modulus. But we know that x is there is x is between a to p, so when we say x is between a to p, so we have a scope to break this integral, right? So we can split this integral, so this is equal to 1 upon mod x minus p integral a to x f of t dt minus a to x f of t dt plus, but again minus, x to p f of t dt minus x minus p f of p, make it complete. Okay, now you can see that one of the integral will get cancelled, so a to x and this will get cancelled. So what I left with is as follows: 1 upon x minus p modulus is this minus x to p can be written as integral p to x. Since f is R integrable, we can always swap the limit minus x minus p f of p. I hope it is okay. This minus sign, when we integral x to p, instead of x to p, we have written p to x. So this is same as 1 upon x minus p. Now what I'll do is as follows. F of t dt minus this x minus p. So let me write down this f of p outside. This x minus p, so it is p times x, so 1 times dt. So you can see that the integration of 1 is t and t will be replaced by x minus p. So instead of writing x minus p, I am writing p to x 1 times dt, this integration. Right. So thus integrations are same, means the limits are same. So we can club this. So if we club, then what we will get is as follows: p to x f of t minus f of p, bracket complete, into dt modulus complete. Since f is R integrable, so modulus of f is also R integrable. So this modulus can be taken inside. So this will be less than equal to 1 upon x minus p. Integral will be outside now, p to x modulus of f of t minus f of p dt. Reason is, since f is R integrable, implies mod f is R integrable. So this property we have used. Well, now we can apply the star over here. Now let's go to the star. We'll start. Star says that if you take any 2 point x minus y, if the distance is less than delta, implies f of x minus f of y is less than epsilon. That's very clear. So now here t and x are points from the closed interval a comma b. So if t minus p less than delta, then definitely this difference is less than epsilon. So that one should understand. So this is strictly less than 1 upon x minus p integral p to x. Now I am replacing it is by epsilon dt. So from star, I have applied the star over here. And now this epsilon can be replaced by, you can see that 1 upon mod x minus p. This is same as epsilon times x minus p. Right? And any number is always less than equal to its modulus. So it is same as 1 upon mod x minus p into epsilon into mod x minus p. So x minus p always less than equal to modulus of it. Now we will left with epsilon. So we have proved that we have started with this difference and we have shown that this difference turns out to be less than epsilon. So therefore modulus of g of x minus g of p upon x minus p minus f of p, this difference turns out to be less than epsilon. This would imply g is differentiable at p. right? So from case 1, if I approach x from the right hand side, I could see that it is differentiable at p. So let me have the second case. So if x is greater than equal to p, strictly greater than I should say now, because we have, this would imply x minus p strictly greater than 0. This would imply modulus of x minus p is x minus p only. Right, now again let us consider what is given. So g of x minus g of p upon x minus p minus f of p, which is same as g of x, we know what is it is a to x f of t dt minus g of p a to p f of t dt upon x minus p minus f of p. So now this time, so let me take this x minus p straight away outside. So it is 1 upon mod x minus p. Now it is integral a to p f of t dt plus p to x f of t dt minus integral a to p f of t dt minus x minus p f of p mod complete. So this x minus p, when I cross multiply over here, then I will get this. And how I got this p, because you could see that this is a, this is b, here x, so p is somewhere here. So a to x can be split to a to p and then p to x. Then you can see that one of the integral will get cancelled. So this and this will get cancelled. So I will only left with the following. So 1 upon x modulus x minus p is basically, you can see that it is p to x f of t dt minus, now f of p, and this x minus p is again can be written as p to x 1 times dt. And you can use the R integrability property now. Now this is same as 1 upon x minus p. This is p to x f of t minus f of p and then it is dt mod complete. So this is less than equal to 1 upon x minus p integral p to x modulus f of t minus f of p mod complete dt. So by mod property, f is R integrable implies mod f is R integrable. And since f is uniformly continuous, so if mod t minus p less than delta, this will definitely less than epsilon. So this is less than mod x minus p integral p to x epsilon dt from star. And now you can see that this is equal to 1 upon x minus p mod complete. This is epsilon times mod x minus p. But bracket x minus p. But x minus p is same as modulus x minus p. So here we can write down here, which is same as epsilon times mod x minus p upon mod x minus p. and which is basically absolute. So somewhere we have less than, so that's remembered. So this would imply therefore modulus of g of x minus g of p upon x minus p minus f of p is less than absolute, right? So from case 1 and 2 we can now say that f is from case 1 and 2 we can say that g is differentiable at p and g dash, what I have to show that is that g dash p is f dash f of p, g dash at p is equal to f at p. But I wanted to show that g is differentiable on open interval a comma b. So p, which we have chosen, is an arbitrary point. So we can say that since p is an arbitrary point, since p is an arbitrary point from open interval a comma b, so this would imply g is differentiable on open interval a comma b, and my g dash x is equal to f of x. So this completes the first fundamental theorem of integral calculus. I just want to do in a case 1 I did here, I said g is differentiable at p, so that's not true, means we cannot say straight away, because here we can say it is between x to b, uh, so I will not write this statement just, so that's fine. Right, because at last we are writing from after case 1 and case 2 we are writing that it is differentiable. Okay, so this completes the first fundamental theorem of integral calculus, and there are, of course, there are some problems based on this theorem. So those problems, and there is a definition called as a primitive definition, and second fundamental theorem of integral calculus. This we will complete in the upcoming lectures. Thank you.